evening. I'm in a most unusual setting. I'm at Boulby mine in Yorkshire, where we're going to find a most unusual observatory. Now, this is a salt mine, and finally we've just found a salt mine on Mars, Chris.
That's right. The Opportunity rover, one of NASA's 2 rovers, has been carrying on its explorations of the planet. It's discovered it's on the shore of an ancient ocean. So we knew the ocean was there from the discoveries we talked about last month, but we now know we're on a site where water flowed into that ocean, a seashore if you like, and it's left salt behind, rather like the pile we can see behind us.
So Mars was once a watery world.
That's right, and the water flowed on the surface. It was there. We had river systems just like the Earth.
One very interesting development had been the discovery of methane in the atmosphere of Mars. Not much, but it's definitely there. Now, methane can't exist for more than about 300 years before being broken down. Therefore, there must be a continual source of supply, and I think 2 possibilities. It could be weak volcanic action, or it could be microbial activity in the antique low-type life. Well, we don't know. I'm not saying there's life on Mars. I'm saying it's a possibility. Time will tell. Watch this space. Something else now. We've been bypassed by a very small asteroid, 2004 FH, which whizzed by in March at only 25,000 miles. It was about 100 feet in diameter. Luckily, there was no danger of hitting us. And another very interesting discovery on the outskirts of the solar system, provisionally named Sedna. And this is, well, near Pluto. We have a whole band of objects making what we call the Kuiper belt. These, Pluto is the largest. But Sedna, about 1,000 miles across at least, is further up than that.
That's right. It never comes as close in as what we think might be the edge of the Kuiper belt. So it might be the first object of what we call the Oort cloud, this vast reservoir of comets that stretches out from around where Sedna is, just beyond Pluto, right out to halfway to the nearest star. A huge distance in solar system terms.
Interestingly, Sedna is very red, a curious kind of world. There may be others out there
and
too.
It's large as well. It's half the size of Pluto, which is much bigger than we'd expect an Oort cloud object to be.
So I fear we've got to admit now that Pluto is a Kuiper belt object and not a proper
Yeah, it's simply the largest one we know out there.
Neither is Sedna. Not further out, Hubble Space Telescope has sent back a marvellous picture.
That's right, called the Hubble Ultra Deep Field, going back to about 800,000 million light years away. So it's the deepest object we're likely to get until Hubble's successor, the James Webb Space Telescope, arrives in 10 years. Now, ignore those bright yellow objects, they're foreground galaxies. It's the faint blue dots that we're interested in, 10,000 very early galaxies, the building blocks of what we see today. And scientists will be looking at them to try and discover exactly how our galaxies form.
I wonder how much further back we'll see. Well, time will tell. And now, on to our main theme. Most people believe that the universe began in the Big Bang, and from this, all matter was created. But we only see a small part of it. The rest is matter we can't see. We call it dark matter. Within and surrounding galaxies such as ours, there's a great deal of dark matter. But what is it? The answer may be mysterious particles called WIMPs, weakly interacting massive particles. Deep in the salt mine, scientists are now hunting for these WIMPs. Here I am, in a lift, going 3/4 of a mile underground in Boulby mine toward this strange observatory. With me now, one of our regular visitors, Professor Carlos Frank.
Hello, Patrick.
First of all, Carlos, why do we think dark matter exists?
Well, I think there are 3 bits of evidence which, in my mind, conclusively demonstrate that dark matter must be there. The first one comes from galaxies, just like the Milky Way galaxy. The stars in the galaxy are going round and round the center, and the reason why these stars don't fly off into intergalactic space is because there is a force of gravity that holds them together. Astronomers realized 30 years ago that the gravity produced by the stars themselves was not enough to keep the galaxy together. And so just like night follows day, we conclude that there must be some more matter that we just don't happen to be able to see, hence the name dark matter, that produces enough gravity to keep the galaxy together.
Well now, we're on our way, 3/4 of a mile underground. Why are we going so deep?
Well, we are going to look for dark matter at the bottom of the mine. And we're actually going to inspect one of the most advanced scientific experiments on Earth. This is an experiment to try and detect particle dark matter. We believe that the most important candidate for the dark matter is an elementary particle. And the reason why we need to go underground to look for it is to shield this very sensitive experiment from the deluge of electrically charged particles that are always raining onto the Earth, the so-called cosmic rays, which would interfere with this very sensitive equipment. So we need to go deep on the ground to filter out these cosmic rays, unwanted background noise. And in essence, we're using the 3/4 of a mile worth of soil between the bottom of the mine and the surface of the Earth as a sort of sieve that would filter out the cosmic rays, allow the dark matter particles to come in, and with a bit of luck, hit the detector and leave a signal, a telltale signal of dark matter.
Dark matter particles. What about things called WIMPs?
Well, they are the same thing. The
Weakly interactive, massive particles. When I say massive, I don't mean they weigh a ton, but they do have mass.
They do have mass. The mass is very, very tiny. It could be, we don't really know what the mass is. It could be insignificantly smaller, for example, than the mass of a proton, which is what nuclei are made of. Or it could be comparable to the mass of a proton, or maybe 10 times bigger than that. But we're talking about tiny, tiny amounts of mass.
What exactly is dark matter then?
Well, we don't really know what it is. I think we do know what it is not. And what dark matter is not. It is not ordinary matter. It is not the sort of matter that stars, planets, or you and I are made of. We call that ordinary matter. And we know that the dark matter has to be something else, something more exotic. Because the Big Bang Theory tells us that only a very small fraction of the matter can be ordinary matter. The lion's share of the dark matter must be probably some fundamental elementary particles of the kind that physics theories predict are required in order to provide a unified theory of the fundamental constituents of matter. Those elementary particles, we believe, are the prime candidates for the dark matter, and that's what this experiment is trying to detect.
And we have detectors at the bottom of the mine.
We have to detect those at the bottom of a mine. There is a possibility that they could be manufactured in a big particle accelerator. Maybe the next generation of particle accelerators might produce dark matter. But while we wait for that, the best bet is to go down a mine, filter out the cosmic rays, and hope that we can catch one of these dark matter particles at the bottom of the mine.
How long has this experiment been going?
It has been going on for about 1 decade. And I think during this time, well, I know it has improved significantly, enormously in its sensitivity, and it may well be that the discovery is now very, very close. It may just be around the corner.
I wonder. Well, on our way now, this strange detector, and it is certainly a most amazing experience. Of course, there are others out there in the world.
There are other experiments. There is, in fact, a race on to see who is the first to detect the dark matter, and this is one of the most advanced experiments, and there is a very good chance that this British experiment might actually get there first.
Let's hope it does. Well, we'll see. Now I'm almost a mile down in the mine in a specially designed laboratory which took years to construct. With me, Dr. Nigel Smith of the Rutherford Appleton Laboratory. Welcome, Nigel. First of all, down here, we are very well shielded, aren't we?
That's right. On the surface, we have cosmic rays that bombard the surface of the Earth. And if you hold your hand out on the surface, you have 1 a second going through your hand. Down here, we have a factor million reduction in that rate, so it's 1 a week. And that shields our detectors from the cosmic rays that are bombarding the surface of the Earth.
What experiments have you got running down here?
Well, we have 2 experiments here. One is called Zeppelin and one is called Drift. The Zeppelin detector behind you is a liquid xenon detector, and that looks at the scintillation light that comes off when a WIMP hits the liquid xenon. The other detector is called Drift, and that's a carbon disulfide detector. And the idea there is actually to look at the directionality of the interaction of the WIMP on the nucleus. The reason is that the Earth moves around the Sun and the Sun moves around the galaxy, and that's happening inside a static halo of dark matter, effectively static halo of dark matter. And the idea is that we could then correlate the interaction, the direction of the interaction with the motion of the Earth through this dark matter halo.
You know, about the last thing I expected to find down here was a pool table. Why?
Well, this is to illustrate how we detect the dark matter particles as they come into our detectors underground. And if we assume that the white ball represents one of the nuclei inside our detector and the red balls represent the WIMPs, represent the dark matter particles, it's like a random game of pool. As the Earth moves through this WIMP halo, these particles are flying past our detectors, and most of them just miss completely. But occasionally, one will hit one of the nuclei in our detector and cause that nucleus to move. And that's what we try to pick up.
How do you pick it up?
We pick it up in a variety of ways. One of the detectors we use looks at light that is created when this recoiling nucleus moves through the target. And another way is to look at the charge that is created. So the two detectors we have here, Zeppelin is a liquid xenon detector. We look at the light that comes out from the detector using very sensitive photomultiplier tubes. Drift is a carbon disulfide detector. We look at the charge that is created. This charge forms a track, and we drift this track down into a readout plane at the bottom.
For 30 years, we've been trying to identify dark matter. Neutrinos, they're considered, and they're dismissed. Then what about MASHOs, or massive compact halo objects? Microlensing has shown that between us and distant stars lie objects we can't see, which must be there because they act as lenses, magnify the light from more distant objects. What are they? Round dwarf stars, large planets, or even small black holes? But only a very few have been discovered, and not enough by far to solve the dark matter problem. Outside the main laboratory, in the salt mine, it's really most impressive. You know, there are about 900 miles of tunnel down here, which is quite something. And with me now in Calvert's Frank, we welcome Professor Bernard Carr of Queen Mary College. Delighted you're with us, Bernard.
Thank you.
Now, we've heard a bit about WIMPs, but I know you've recently on what we call MACHOs.
A MACHO is an acronym for a massive compact halo object. And I should explain that there are two broad categories of dark matter candidates. One are the elementary particle candidates, called the WIMPs, which we've already heard about. The other category of dark matter candidates are supposed to be formed from ordinary baryonic material. Now, by baryonic material, we mean the matter which makes up protons and neutrons.
You and me.
You and me. Now, people started off asking whether ordinary matter like that could explain the dark matter problem. But we think the answer is that it can't. And one of the first experiments that people did in looking for MACHOs was to look for their gravitational lensing effects. And there's an effect here which is called microlensing. And the idea is very straightforward, that if we're looking at a distant star, and if one of these MACHOs passes the line of sight of the star, then you predict that the intensity of the star, the brightness of the star, is first going to rise and then it's going to fall, because the bending of light by the gravitational field of the MACHO has that effect. So about 10 years ago, people started looking for this microlensing effect. And the result of those searches was that they did find microlensing. But what they found was, there have been about a dozen events which have all the signatures of being due to gravitational lensing. But what was frustrating was that the frequency of these microlensing events showed that you couldn't have all of the dark matter, all of the halo dark matter in these MACHOs. It was something like 20% of the halo dark matter appeared to be in these MACHOs, more than is in visible form, so there was something dark there, but not enough to make up the halo in total. And so in a way that was rather frustrating, but in another way it's really rather good, because it means that we seem to have a combination of the WIMPs, which of course they're searching for here in Boulby, and the MACHOs, which at least exist in enough abundance to be interesting.
And of course, one failed candidate here is the neutrino.
Yes, I began my career working on neutrinos about 25 years ago, because neutrinos were very attractive candidates for the dark matter, for no other reason that we know neutrinos exist. We don't yet know that WIMPs exist, but we know neutrinos exist. But 25 years ago, it wasn't really known whether the neutrinos had a mass, sufficiently large mass to be the dark matter. And what convinced me and my colleagues that neutrinos was not the answer was simply we carried out computer simulations of how the universe would have evolved if the dark matter was actually made of neutrinos. And what the computer simulation showed was that the neutrinos are moving so fast, that's why they call hot dark matter, because they move very fast, that they would just not collect in galaxies. If neutrinos were the dark matter would just flow away from galaxies, and the galaxies would just evaporate in a puff of smoke. So if the neutrino had been the dark matter, our universe wouldn't look anything like it does. We knew that 25 years ago, and then very interestingly, 2 or 3 years ago, it was experimentally proved that indeed the neutrino does have a mass, but it's tiny. It's about 1,000 times smaller than would be required for it to be the dark matter.
Well, what can we learn here from the cosmic microwave background, the radiation coming in from all sides?
Well, one of the most, I think, spectacular developments of the last 2 years has been the ability to measure very, very precisely how much dark matter the universe contains. And the fascinating aspect is that the data used to make this measurement comes to us directly from the Big Bang in the form of the microwave background radiation that you just mentioned. This is just the heat left over from the primeval fireball, which as the universe expands has been cooling down, and we see today as a microwave background radiation. Now, this tells us directly about what happened when the universe was very young, because the microwave background radiation was emitted when the universe was a mere 300,000 years old. It sounds like a lot, but it is actually very short compared to the age of the universe. And in human terms, it is equivalent to 1 day in the life of the young universe.
Indeed.
Now, what we know now about the microwave background radiation is that it is not perfectly smooth. When we look at maps of the microwave background radiation, we see a pattern of hot and cold spots. Now, these hot and cold spots merely reflect the fact that already at this early epoch, the seeds for galaxies were being formed, and these seeds are small clumps of dark matter. So this pattern of hot and cold spots is simply a reflection of the fact that dark matter had already begun to clump at these very early times. And so by studying the properties of these hot and cold patterns and microwave background radiation, physicists are able to measure with exquisite accuracy how much dark matter the universe has. So that's a very, very exciting development. We now know what we're looking for and how much there should be.
Well, we are down here now in Boulby mine where they're looking for these particles. How long do you think it will be before we really have the full answers?
Well, in terms of looking for WIMPs, I suppose hopefully one would expect on a time scale of 10 years that one would hope to have positive results, because apart from the Boulby group, there are a number of groups looking for this, and if the WIMPs are there, I think we can hope to find them within that sort of time scale. But the point is that even if you haven't found them, it's still very useful because you're constraining their properties. As regards the machos, I think we really more or less know in terms of lensing that they don't make up most of the halo dark mass, but we still have the problem of explaining what does make up that small fraction of dark macho mass which is required to explain the microlensing results. And
one thing that strikes me, we talk about baryonic matter, that's you and me, and non-baryonic matter, which could be this dark matter. Is there any chance of any real interaction between the two?
Well, there is, definitely. But they interact through gravitational interactions. I think Bernard finds it frustrating that the machos are just a small fraction. I find it exceedingly reassuring because I am convinced that the WIMPs must exist. And the reason I am convinced that the WIMPs must exist is because otherwise the universe would not make sense. And that is because what we see when we look out with our observatories and our telescopes is a very beautifully structured universe lit up by stars and galaxies. Yes. Now the galaxies are essentially a reflection of processes that have happened in the dark matter. So the dark matter begins to clump very early on, and we see the consequence of this in the microwave background radiation. And then soon after the radiation is emitted, ordinary matter begins to fall into these clumps of dark matter, where eventually it cools and it turns into stars, and then the stars collect together, making beautiful galaxies. So there's definitely a two-way interaction between the dark matter and the ordinary matter, because the ordinary matter follows where the dark matter wants to go.
Can I just say, I don't find it frustrating that the fraction of machos is so small.
Yes.
To me, the great challenge is that it requires a combination of both the candidates provided by the particle physicists and the candidates that provided by the astrophysicists. And even though the machos do not provide most of the dark mass, nevertheless there seems to be more dark mass in that form than in the visible baryons like the visible stars. So it's a tremendous challenge to explain both of them.
Dark matter is a puzzle, but dark energy is even more so.
I think dark energy is the last actor that's come onto the stage, which is the cosmos, and it's made its appearance very recently, causing the whole play to go into confusion. We know that dark energy is there. We just confirmed it in the last 2 years. It's a newcomer, and it is very distinct from dark matter. It's a force that causes the universe, the universal expansion, to accelerate. We don't know what it is. I don't know if Bernard knows what it is. I certainly do not know what the dark energy is.
Do you, Bernard?
Well, one of the theories for this dark energy is that it may have something to do with the cosmological constant, which was a term that Einstein introduced into his equations of gravity.
And then abandoned.
He originally abandoned it. I mean, he introduced it because he wanted the universe to be static. When the universe was found to be expanding, he said it was his greatest mistake. But now it looks as though there may be a cosmological constant anyway, in which case his greatest mistake was saying it was his greatest mistake.
You know, we may not have the full answers, but we are doing our best to find out. Here we are, a mile down, studying these things in the most unusual observatory, and we've made great progress, and I think before long we'll learn a great deal more than we do now. We're living in exciting times. Bernard, Carlos, thank you very much indeed.
Thank you, Patrick.
When I come back next month, we are coming more down to earth and talking about the formation of stars. So from Boulby Mine, from all of us, good night.
Making the film Schindler's List had a profound effect on director Steven Spielberg and caused him to set up the Shoah Foundation. He talks about the experience next here on BBC Two.